So this is part 7 of the course. It's described as conservation of mass and energy. And in the last part of the course, in part 6, what we done was we applied the first law of thermodynamics to a closed thermodynamic system. And what we're doing in this part of the course is we're applying the first law to open systems. That's a system in which we have a mass flow of the working fluid coming in and a mass flow of the working fluid coming out of our open system or control volume. And it can potentially take energy with it coming in, and it can potentially take energy with it coming out. The theory, so this is the expanded version of the first law applied to open systems. And the theory here is based on a couple of fundamental principles of physics called the conservation of mass and the conservation of energy. And that's why this part is described as conservation of mass and energy. So what we're going to do is we're going to introduce the conservation of mass principle. We've already introduced the concept of the conservation of energy. We're going to introduce and derive the steady flow energy equation that we've just seen in the previous slide, and then do an energy analysis on steady flow systems. So the conservation of mass is a fundamental principle of physics, very similar to the conservation of energy. A simple analogy would be if we had 1 kilogram of water and 1 kilogram of salt, mix them together, we get 2 kilograms of a saline solution. And that's a process that has taken place. And during that process, mass is conserved. And that's what the conservation of mass is telling us. So it reads here, the principle of the conservation of mass states that mass, like energy, cannot be created or destroyed, but only changed in form. Whatever happens, the mass of the substance before is the same as the mass of the substance after. This is called the law of conservation of mass. Example there would be if a piece of wood is burnt, the mass of the log and the oxygen used in the burning will be the same as the mass of the gases produced and the remaining ashes. Another example, it would be 100 grams of water is put into a pot and boiled. Eventually, all the water will boil away as steam. If you collect all the steam and measure it, its mass would be exactly 100 grams. And the exception to this is nuclear reaction. According to Einstein's famous equation, E equals mc squared, we can take an amount of mass and we can turn it into energy. But beyond nuclear reaction, for all other thermodynamic processes, we can assume that the conservation of mass and the conservation of energy both hold true and hold separately. Einstein's equation, E equals mc squared, relates the mass of energy in nuclear reactions, where c is the velocity of light. In almost every case in engineering thermodynamics, with the exception of nuclear reaction, no conversion between mass and energy occur. Therefore, the principle of conservation of mass and energy holds separately.
Clear. Air is let into the gas turbine through an air intake. The air is prone to contamination or having some unwanted particles which can harm the system and degrade the.
Apologies, just knocked the sound off on that. So in these systems, we're dealing with steady flow processes. A steady flow process is a concept in thermodynamics often associated with systems where fluid, gas, or liquid flows continuously through an open system or control volume. In other words, a section of pipe, pump, turbine, boilers, condensers, heat exchangers, nozzles, etc. In a steady flow process, the fluid properties at any given point within the control volume do not change with time, meaning that the mass flow rate and energy flow rate and other properties remain constant over time. A steady flow rate is a flow rate that does not vary with time, and a non-steady or unsteady flow rate varies with time. So in a power plant, for example, you've got a boiler, condenser, turbine, feed pump. They can all separately be regarded as open systems and analyzed as open systems. So when you switch on a power plant, it ramps up and then it runs on steady state. It could run for In some cases, power plants have ran continuously for two to 3 years before they're taken out of commission for maintenance purposes. So during that time, the mass flow rate and the energy flow rate is constant all the way through. And that's what we mean by steady flow processes. Most of these processes, thermodynamic processes, would be steady flow processes, and it simplifies the theory. We mentioned energy flow rate and mass flow rate there. So what I want to do now is just explain what mass flow rate is and energy flow rate and volumetric flow rate, and then apply the concept of mass flow rate to the conservation of mass. So mass flow rate is the amount of mass flowing through a cross-section area per unit time, denoted by m dot in kilograms per second. So imagine a pipeline and you've 1 kilogram of the working fluid passing by a point every second. So you'd have a mass flow rate of 1 kilogram per second. Volumetric flow rate, on the other hand, is the volume of a fluid flowing through a cross-section area per unit time, denoted by V dot in meters cubed per second. So now, if you can imagine a meter cubed per second of fluid flowing past a particular point in the pipeline every second, you would have a volumetric flow rate of 1 meter cubed per second. Volumetric flow rate and mass flow rate are related to each other by density here. So if we divide m dot by density, we get V dot, or if we multiply V dot by density, we get m dot. But they're also related to each other by specific volume, because specific volume is the inverse of density. Now, energy flow rate is the rate of energy carried by the fluid flowing through a cross-section area per unit time, denoted by E dot in watts. So it's the energy per unit mass multiplied by the mass flow rate. And when you cancel the units, you end up with joules per second or watts. So on this slide, what we're doing is just simply deriving what mass flow rate theoretically. And if we imagine a control volume in a pipeline around maybe a nozzle like this, so we've got the control volume on, there's a section of pipe, and we draw a box around it and consider that our open thermodynamic system, the fluid flowing through and flowing out. And so an open system is referred to as a control volume. These are our controlled surfaces around here. And if we consider the controlled surface at the outlet and just zoom in on it, that's what we get down here. And for a differential amount of mass flow rate crossing that surface, it's the density by the normal velocity component acting perpendicular to the controlled surface by the differential area dA subscript C over which it acts. If we want the total mass flow rate acting across that controlled surface, in other words, right across this section of pipe, then we integrate right across the pipe. And the integral works out at density by an average velocity by the total area of the control volume. So when we're given a velocity in a pipeline, it's the average velocity, but we don't write the subscript average in there. So this is the way we would calculate mass flow rate going through a pipeline: the density by the velocity by the cross-section area of the pipe. And similarly, it can be shown that the volumetric flow rate is simply the velocity by the cross-section area. So we drop the density in that case. So applying the conservation of mass principle to a controlled volume, we say that the mass that enters through the boundary minus the mass that leaves the boundary equals the increase or decrease of mass within the boundary. So the mass coming in here minus the mass going out here will equal any accumulation or depreciation of mass in the control volume. Mathematically, it's expressed like this in kilograms. But in terms of flow rate, mass flow rate, we say that the rate of which mass enters through the boundary minus the rate at which mass leaves the boundary equals the rate of change of mass within the boundary. So the same, but just in terms of flow rate. And mathematically, it's expressed like this. So the rate of change of mass within the boundary for steady state flow, that should equal 0. It means we're not accumulating any mass in here, or we're not depreciating the mass in there. It stays constant. So that m dot in minus m dot out equals 0. Okay, so m dot in equals m dot out. If we want to break it down into density, velocity, and area, we can express it like this. For an incompressible flow where the density doesn't change, we can simply express it in terms of volumetric flow rate as well. If we're dealing with multiple inlets and outlets, we sum them up. So we say the sum of all the mass flow rates coming in should equal the sum of the mass flow rates going out. Otherwise, there will be an accumulation or a depreciation of mass in the control volume. So the steady flow energy equation is basically the first law being applied to open systems. It's an equation to fluid dynamics derived from the first law of thermodynamics for analyzing systems where fluid flows in a steady state manner through open systems, also called control volumes. Energy can be transferred by heat, work, mass flow only. In steady state process, total energy entering a control volume is equal to the total energy leaving the control volume. So we're looking at the same thing, but in energy terms. So we're saying the rate at which energy enters the system minus the rate at which energy leaves the system equals the rate of change of energy within the system. And for steady state flow, there should be no rate of change of energy in the system, no accumulation or depreciation. So the energy in should equal the energy out. So the energy coming in can be in the form of heat, it can be in the form of work, it can be in the form of mass flow in its different shapes and forms. And the energy out can be in the form of heat, work, or mass flow in its different forms as well. So applying the first law of thermodynamics to an open system or control volume, we're dealing with a single inlet and a single outlet. It's basically the rate of heat transfer minus the rate of work being done by the system equals the rate of energy, change of energy in the system in the forms of enthalpy, kinetic energy, and potential energy. So to the derivation for that steady flow energy equation for a simple compressible system like a piston cylinder. So when we say compressible system, we're looking at the likes of a piston cylinder device where you compress and expand, and there's a boundary work being done, and that's the main focus. And for that type of system, the total energy in the system can come in the forms of internal energy, kinetic energy, potential energy. Generally, these two were small or negligible, so we were generally dealing with a change in internal energy. If we express them per unit mass, they look like this. So specific internal energy, so it's the V squared over 2. We drop the mass. For kinetic energy, we drop the mass for potential energy. So, so this is the total energy that we can get for a simple compressible system per unit mass. But if we want the total energy of a flowing fluid system, that's a system like an open system that has fluid flowing through it, we also need to add in the flow work or flow energy, which is pressure by volume, and or P by small v, which in its specific formats. So that's kilojoules per kilogram. We see there's a relationship there. U plus PV is actually enthalpy. So we add enthalpy in there instead of U plus PV. And we have this in kilojoules per kilogram. If we want to express it in terms of kilojoules only, we multiply by mass. If we want to express it in rate form, we multiply by mass by m dot and get kilowatts. So the rate of energy transport is expressed like this. It's m dot multiplied by enthalpy by specific kinetic energy, specific potential energy. And between the difference between between an inlet and an outlet, it would be expressed like this. And if we do an energy balance, we're saying that the heat coming in minus the work going out equals the change of energy in the system in these different forms. And that's the steady flow energy equation. And what we want to do is we want to apply that to different thermodynamic systems. So for closed systems, just to reinforce once again, the first law looks like this. It's the heat applied minus the work done by the system equals the change of energy in the system. So we apply heat to that gas, it expands and does work, and that changes the internal energy in the system here. For steady flow systems, we apply heat to the system, and there's work done by the system potentially, and then that changes the energy in the system itself, which can come in the change of enthalpy, kinetic energy, and potential energy. So this slide here just outlines the unit consistency for this equation. So the heat transfer rate is in kilojoules per second or kilowatts. The rate of doing work, which is power, is in kilowatts or kilojoules per second as well. The mass flow rate up here is in kilograms per second. And the enthalpy, specific enthalpy, would be in kilojoules per kilogram. So when we multiply m dot by h, the kilograms cancel and you're left with kilojoules per second, which is the same as up here. So that unit consistency is fine. So how do we go from v squared over 2 equal, which would equal m squared over s squared? How would we make sure that that's consistent with the other units and end up with joules per kilogram? Well, the way to think about it is kinetic energy and potential energy, their ultimate units are the joule. The SI unit is the joule. So if we express kinetic energy and potential energy per unit mass, we've got joules per kilogram. So V squared over 2 can be expressed as joules per kilogram. And G by Z, which is specific potential energy, can also be expressed in the form of joules per kilogram. So mathematically, this is actually right. We can go from meters squared over second squared to joules per kilogram. But that's the easier way to think about it. It's that the potential and kinetic energy are in joules. And if we want to express them in their specific form, it's joules per kilogram. So we've got joules per kilogram over here, kilojoules per kilogram, and the same here. So that gives us our unit consistency for the steady flow energy equation. So steady flow devices are devices that are designed for continuous operation. And there's a list of them here: pumps, compressors, fans, turbines, heat exchangers, nozzles, diffusers, boilers, condensers, throttle valves, mixing valve chambers, and so on. So I want to apply the steady flow energy equation to some of these different devices and show how it's applied. So let's start with the nozzle. The nozzle is a device designed to control the direction or characteristics of a fluid flow, especially to increase velocity, as it exits or enters an enclosed chamber or pipe. Nozzles increase the velocity of a fluid at the expense of pressure. So as fluid is flowing through a pipeline and it comes up to a nozzle, the velocity increases, but the pressure drops. It's like if you have a garden hose and you pinch the top of the garden hose, the fluid will come out, the water come out quicker at a higher velocity, but the pressure will reduce. So that principle is used in rocket engines, for example. Nozzles in rocket engines accelerate the exhaust gases to produce thrust. Jet engines do the same. Turbojet engines use nozzles to accelerate exhaust gases to create thrust. Fuel injectors, these nozzles atomize fuel into fine droplets for efficient combustion into internal combustion engines. And gas turbines, nozzles direct the flow of the hot gases to turbines, converting thermal energy into mechanical work. And a diffuser is the opposite of a nozzle. So the nozzle looks like this. The diffuser is designed the other way. It's like flipping the nozzle, and you get less velocity coming out, but you get higher pressure. So diffuser is a device that's designed to slow down the velocity of a fluid, in other words, a gas or a liquid, and increase its pressure. This is essentially the opposite function of a nozzle, which accelerates fluid and decreases its pressure. Diffusers increase the pressure of a fluid at the expense of kinetic energy. This is achieved through a gradual expansion of the cross-section area of the flow path. Diffusers are widely used in various engineering applications, such as in gas turbines, jet engines, HVAC systems, and fluid systems. So this is a gas turbine here. And air is compressed when it comes in, and it's mixed with gas, and the energy produced from the ignition of that mixture drives the turbine blades and produces electricity. The hot exhaust gases come out through a diffuser, and what that does is it slows them down and increases their pressure. And those gases can then be used in a boiler to heat up water to create steam to drive a gas turbine. And that's called a combined cycle gas turbine system. And it's the type of system that's used in the Poolbeg power station down the Rings End. And I have an animation of a similar system to that, which I'll show in a few moments. So with nozzles and diffusers, we look at the steady flow energy equation. There's no significant heat transfer. So the fluid is going past, or the exhaust gases will go through here very quickly, so that there's no heat exchanged with the environment as such, no heat transfer loss to the environment. So the heat transfer rate is small or negligible. There's no work involved in these processes because there's no moving parts. There's no change in potential energy because there's no significant height from the inlet to the outlet. And so the steady flow energy equation reduces down to the change in enthalpy equals the change in kinetic energy. And remember, the component of enthalpy is pressure. So basically, there's a change in pressure and there's a change in velocity, which we would expect. So here's an example. Consider a gas entering a diffuser with the following conditions. There's a velocity of 300 meters per second coming in, a velocity of 150 meters per second going out. So the velocity is decreased as you'd expect. The inlet enthalpy is 300 kilojoules per kilogram. So we want to find the outlet enthalpy. So this is our equation here. We've just rearranged it. And to get H2, it ultimately equals 333.75. So our enthalpy is increased. And remember, pressure is a component of enthalpy. So the pressure is increased and the velocity is decreased, which we would expect. A turbine is a mechanical device that extracts energy from a fluid, usually a gas or a steam, and converts it to useful work. Typically rotational mechanical energy. Turbines are widely used in power generation, propulsion systems, various industrial applications where converting fluid energy into mechanical energy is necessary. And the two common forms there are steam turbines. These turbines use steam as working fluid. They're commonly used in power plants to generate electricity. And then gas turbines use hot gases, often from burning fuels such as natural gas or diesel, as the working fluid. They are widely used in aircraft propulsion power plants, where they can be combined with steam turbines in combined cycle plants and other industrial applications. So in turbines, fluid exerts forces on the blades and work is done by the system. So energy is extracted from the fluid. Excuse me. The steam comes in, it rotates the blades, and work is produced by the system, and then low temperature steam comes out. And so once again, there's no significant heat transfer because the steam is moving there through the system at a high velocity. So this is saying that there is work being done by the system. It's being done by the turbine or added to if it's a pump. And the change in kinetic energy is often small. Note that usually the kinetic energy is much more significantly smaller than the change in enthalpy and is sometimes neglected. So there's no potential energy. We can drop that component there and heat transfer. So we do have work and we do have kinetic and enthalpy components in there. So steam enters a turbine at 10 megapascals and 500 degrees with a velocity of 50 meters per second. It exits at 10 kilopascals with a velocity of 150 meters per second. Calculate the power output of the turbine, assuming adiabatic conditions, in other words, no heat transfer. Mass flow rate of the steam is 10 kilograms per second. So we want the work. We have the mass flow rate. We need to know the enthalpy change, and we need to work out the velocities as well. So using the steam tables, we're assuming that the steam coming in is superheated, which it should be. So at 10 megapascals and 500 degrees, it works out at, from the steam tables, 3375.1 kilojoules per kilogram. And then at 10 kilopascals, we're assuming it to be saturated steam at exit. So it's on the verge of condensing. So it would be Hg from the tables. And that's 2583.9 kilojoules per kilogram. And we work out our inlet and outlet velocities there. So when we add those values in there, the work produced is 7812 kilojoules per second or kilowatts. So we can see that there's the enthalpy is high coming in, and then it's significantly lower coming out. And most of that energy has been converted to work. We'll also see that the velocity has increased coming out as well. But when we look at the components there, we see that the change in internal energy is much larger than the change in velocity. So in some cases, we can neglect the change in velocity of the fluid, the kinetic energy of the fluid if we want to. So we've introduced the concept of the diffuser and the turbine, the gas turbine and steam turbine. So this is what we call a combined cycle gas turbine system. So what we have is we have a gas turbine up here, and compressed air is brought in, and it's mixed with natural gas, and it's ignited, and the energy drives the turbine and produces electricity in the generator over here. And then the exhaust gases are put through a diffuser to reduce their speed, increase their pressure. That will help generate steam in the boiler, and the steam comes out and it drives the turbine. So it's a combined cycle gas turbine system, and it's the type of system that would be used down in Poolbeg, which provides most of the energy to the Dublin region. Okay, so we're going to continue part 7 of the course that's described as conservation of mass and energy. And this is basically where we applied the first law of thermodynamics to open systems. Open systems where we have a mass flow coming in of the working fluid and a mass flow going out, potentially taking energy with it coming in and potentially taking energy with it going out. So you can see the first law is a more expanded version of the first law that was applied to closed systems because we're taking into consideration kinetic energy, potential energy, and flow energy as well. So we applied steady flow energy equation to nozzles, diffusers, and turbines. And what I want to do now is apply it to boilers, compressors, pumps, heat exchangers, mixing valves, or mixing chambers, and throttle valves. So a boiler, basically, let's start with a boiler. It's basically a glorified kettle. It's a device used to convert water into steam by adding heat. It's a crucial component in power plants and various industrial components. So we consider the steady flow energy equation, and we can simplify it by saying that there's no significant flow rate going through a boiler. So the kinetic energy component is negligible. There's no significant height difference to consider either. So the potential energy component is negligible as well. It doesn't produce any work because there's no moving parts. So the steady flow energy equation reduces down to the heat transfer rate equals the mass flow rate by the change in specific enthalpy. So an example here, if water enters a boiler at a pressure of 2 megapascals and a temperature of 240 degrees C, and is heated to become superheated steam at 2 megapascals and 400 degrees C. Determine the heat added to the water per kilogram. So the water enters the boiler as compressed liquid water here and ends up over in the superheated region on the way out. So for table A7 at 2 megapascals and 240 degrees C, which is the compressed liquid water table, the enthalpy is 1039.2 kilojoules per kilogram. In the outlet, we use table A6 for superheated steam, and at 2 megapascals and 400 degrees C, the enthalpy is 3248.4 kilojoules per kilogram. We're asked to express this heat added per kilogram, so we can drop the mass flow rate in here and just deal with specific enthalpy. And the value is 2209.2 kilojoules per kilogram. Steady flow device applied to compressors and pumps. Compressors and pumps increase the pressure of a working fluid by work input to the system by a rotating shaft, and it extracts energy from the surroundings. So what that means is we plug it in, we use electricity externally to drive the pump. And a compressor is mainly dealing with gases, and a pump is mainly dealing with liquids. And once again, the potential energy is regarded as negligible. There's no significant height difference from one side of the pump to the other. The change in kinetic energy is often small in comparison to the change in enthalpy. So we can consider whether we want to ignore it or not. The heat transfer rate is insignificant again, unless otherwise stated. And the rate of doing work is not equal to zero. So there is work being done by the pump. So the rate of doing work, which is the power, equals the mass flow rate by the change in enthalpy in kilowatts. So let's look at an example here. Pump increases the pressure of water from 100 kilopascals to 500 kilopascals. The water enters the pump with an enthalpy of 420 kilojoules per kilogram and exits with an enthalpy of 430 kilojoules per kilogram. The inlet velocity is 2 meters per second and the outlet velocity is 3 meters per second. The inlet and outlet elevations are 5 meters and 8 meters, respectively. The mass flow rate of the water is 0.5 kilograms per second. Determine the power required by the pump. So that's all those values outlined there. But these are the ones that we really need to calculate the power. It's the mass flow rate by the change in specific enthalpy. And when we put those values in there, we end up with basically 5 kilowatts. If we did consider the potential and kinetic energy aspects to it, we do have the values there to calculate them and add them in. And if we do, it works out at 5.016 kilowatts. So you can see there's not a significant difference by adding them in this particular case. So, steady flow device applied to a heat exchanger. A heat exchanger is a device used to transfer heat between two or more fluids without mixing them, and are critical components in numerous industries, ensuring efficient heat transfer to maintain optimal operating conditions and improve energy efficiency. So you can see here you've got cool water coming into the heat exchanger and it goes out warmer. And that's because it's taking heat from a hot water system that comes in and essentially goes out uh, cooler afterwards. And where they would be used would be heat recovery systems, for example. If we look at the animation here, what you have quite often in new builds now where they're using air source heat pumps that sit outside the home, they're bringing energy from the air and bringing them inside the house. But in order for those systems to work, you need fairly well insulated homes, what they call passive homes. And because of that, the house doesn't breathe naturally like other houses would. So you need a mechanical ventilation system like the one that's shown in the illustration. So what that will do is take the stale air out and push it out of the house, and it will bring fresh air coming in. But there's a heat exchanger along the line where the two streams meet, and the heat from the stale air is transferred to the fresh air coming in to try and recover some of the energy before it's lost from the house. They're also used in many processes in the industry. So, for example, you have a process that generates a lot of heat and you need to extract that heat to maybe protect the machines, for example. But that energy could be used somewhere else in the factory as a space heating system. So heat exchangers would be used in those situations and many other reasons too. Power plants, for example, use heat exchangers for condensing steam from turbines, and we've seen them previously. Okay, so an example there, for most heat exchangers, we can make the following assumptions. There's no work being done by them. Once again, no moving parts. The kinetic energy is negligible because the fluids aren't flowing at a significant velocity, and there's no particular height difference between one flow from one end of the flow to the other. So for the hot fluid that's losing heat, we can calculate the heat transfer rate by multiplying m dot by the change in specific enthalpy from the inlet to the outlet. For the cold fluid gaining heat, we can calculate the heat transfer rate by this time multiplying the flow rate for the cold stream by the change in enthalpy from the outlet to the inlet. And what we can also do in these equations is we can express the specific enthalpy in terms of the specific heat capacity and the temperature. So we look at that now. So heat exchanger transfers heat between two streams of water. The hot stream enters the heat exchanger at 150 degrees with a flow rate of 1.5 kilograms per second that leaves at 80 degrees. So that's 150 there coming out at 80 degrees. The cold water stream enters the heat exchanger at 25 degrees here and leaves at 70 degrees. The specific heat capacity of the water is 4.18 kilojoules per kilogram Kelvin. So assume no heat losses to the surroundings. Calculate the heat transfer rate in the heat exchanger. So the heat loss by the hot stream is equal to the heat gain by the cold stream, but assuming there's no losses to the surroundings. And we can expand that in terms of the enthalpy and the mass flow rates. So we'll take one or the other. We can take the hot stream or the cold stream. So we'll take the hot stream, but we'll express it in terms of the specific heat capacity and the temperatures because we have those values. So we have the mass flow rate of the hot water by the specific heat capacity for water in general, and then the temperature difference from the hot inlet to the hot outlet. And what we end up is 438.9 kilowatts. So the heat transfer rate in the heat exchanger is 438.9 kilowatts. This is a mixing chamber. A mixing chamber is a device where two streams are mixed. And typically there's no heat transfer rate because the fluids are continuously moving and they don't get an opportunity really to transfer heat to the surroundings, and the pipes may be insulated as well. There's no working parts, so there's no work being done. And the kinetic energy is not significant. Again, they're not moving at high velocities, and no potential energy is generally regarded as negligible. Again, when we apply the steady flow energy equation, what we do is we sum up all the mass flow rates by their enthalpies on the inlets, and that equals the mass flow rate at the outlet by the enthalpy at the outlet as well. If we're dealing with two streams, we have the mass flow rate of the first stream, let's say the hot stream, plus its enthalpy, multiplied by its enthalpy, plus the mass flow rate of the cold stream multiplied by its enthalpy. And then that equals the two flow rates together and multiplied by the enthalpy of the outlet stream. So we've got hot water coming in, cold water going out. They're mixing and coming out up here. So what we effectively want to do is know what the mass flow rate and the enthalpy, or maybe the temperature coming out here is. So consider a shower where hot water is coming in at 60 degrees. It's mixed with cold water at 10 degrees. If the ratio of the mass flow rates to the of the hot to the cold water, m.1 over m.2 equals 1. So that basically means that m.1 equals m.2. The flow rates are the same. Determine the temperature of the desired steady stream of water at the outlet T3. Assume heat losses from the mixing chamber to the surroundings are negligible. So this is the equation: mass flow rate of the first stream by its enthalpy plus the mass flow rate of the second stream plus it by its enthalpy equals the mass flow rates combined plus the enthalpy at the outlet. So what we're going to do is we're going to express the enthalpy in terms of specific heat capacity and temperature. Put that into the equations here. We're going to cancel out the specific heat capacities because they're the same value, and we're left with the temperatures in there. And then we just rearrange it to just multiply T3 into these brackets to clean it up. Now, if we rearrange to get m.1 on one side and m.2 on the other side, and we transpose it to get the ratio m.1 over m.2, which equals 1, we can express it then in terms of the temperatures that we're dealing with. So we plug the values in for T2 and T1, and then when we rearrange it and work it out, it works out that T3 works out to be 35 degrees Celsius. So basically what that means is that we've a flow rate of hot water coming in at 60 degrees here. We have a flow rate of cold water coming in at 10 degrees here. Those two flow rates equal each other. And then the outlet is the flow rate is going to be the sum of those two, but the temperature is going to be 35 degrees. So that's basically 60 plus 10 divided by 2. And then finally, for this section, the final steady flow device that we look at is the throttling valve. And a throttling valve is any type of flow control device that causes pressure drop in the fluids as it passes through a valve. So you've got globe valves and butterfly valves and so on. An orifice plate is a system that causes a pressure drop so we can measure flow rate, because flow rate is proportional to pressure drop. And this would be treated as a throttling valve. You have these porous plugs that slow down the flow and maybe turn it from turbulent into laminar. And they can be considered a throttling valve of a sort. You have this type of butterfly valve here, or you have a gate or globe valves of different configurations as well. So once again, it's regarded as an adiabatic process because there's no heat transfer in or out, or at least it would be significant because the fluid is moving through the system. No work done by the system, no moving parts as such, no change in potential energy, and the increase in kinetic energy is also ignored. So it's what we call an isenthalpic device. So the enthalpy on one side of the valve is the same as the enthalpy on the other side of the valve. And we can express that in terms of its specific internal energy, the pressure, and the specific volume. So we might want to know what the pressure is on the other side of the system. So we have the pressure on one side, and we can find the specific internal energy, some steam tables perhaps, and specific volumes, we can find that second pressure. And that's the end of this section.